In both section 16.1 and 16.2, we were doing double integrals in the rectangular coordinate system. But believe it or not, there are a lot of times where the rectangular coordinate system is not very good and the polar coordinate system is much better. But we have to think about how this is going to work. So when we did double integrals of f of x, y, dA, dA was understood to be dx dy or dy dx, depending on whether you wanted a horizontal or a vertical rectangle. And actually, I'll just throw those in there to remind you how that goes. So now, how would that change? How would dA change if we're now in the polar coordinates? How's that going to work? All right, so first of all, we know that x equals r cosine theta and y equals r sine theta. We learned that when we learned the polar coordinate system, usually in Calc 2. And then x squared plus y squared equals r squared. So that's fairly straightforward. I mean, we know how to convert from a standard function to a polar function. No problem, right? But now what about dA? All right, so to think about the dA, that requires a little bit of geometry. So when you think about dA, you're looking at small squares. I drew a little grid in here so you could see. So x is going from A to B, y is going from C to D. We have this grid, and the length of that side is dx, and the length of this side is dy, and of course we're letting it be infinitesimally small because we're letting the number of pillars that are stacked on top of this in the third dimension go to infinity, right? Okay, so dA is dx dy or dy dx, right? Just a reminder, dy dx is vertical for the rectangle that you draw in the region, and dx dy is horizontal. It's just a review of that because everybody always forgets. Okay, now, but how would that grid change for polar coordinates? Okay, so for polar coordinates, it comes down to the pole. That's where polar gets its name. So there's a grid that's coming off of the polar coordinates of the pole. Oop, I drew that one too big. No, there we go. I'll draw another one in there. And everything's tied back to that origin. Sorry, this is not perfect. Okay, and then you have rings around that origin. So dA is actually a section right in here. Right? Okay, so how do we find that? Oh, actually, before I go any further, let me just show you. The R is right here. R equals A is right here. That's the ring of radius A, and R equals B is out here. So it's called a polar rectangle, this little piece. It looks like a square, but it's not. It's actually like a little piece of a wedge, right? It's called a sector. So R is going from A to B. Theta is your angle. So theta starts over here at theta equals A, and it plugs through, right, along the pole, chug, 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 and ends up over here at theta equals, actually this was alpha. Theta equals alpha, theta equals beta. They like to use Greek letters for angles. Okay, so why is it called a polar rectangle? Well, it's a polar rectangle because r and theta are constants, right? Or they're moving between constant values, right? Sorry, they use constants. I didn't leave room for the word use. Okay, so let's zoom in on this little piece, actually this kind of wedge right here. Let's zoom in a little bit more in the next picture. Okay, so there it is. Look at that. All right, so we have this section, right? So we want to look at it. This piece right here. And then we're going to zoom in even more, and it's this piece right here. This is that piece. Okay. And that's the little section we're trying to look at. All right, well, how does that compare? Well, we can see that we have a change in angles right here, right? So this, if you will, is the change in your thetas, right? Because you're going from one angle to another angle, right? It's right here. They wrote it as delta theta, right? So you can write it down here, delta theta, or you can write it up here. Either way, right? That's your change in your angle. But then we also have a change in the radiuses, right? So that's delta r. So if you will, this little piece right here is the change in your radius. This little piece right here is the change in your theta, if you want to think of it that way. Here, that'll be easier. Okay, so then how do we find the area? Okay, well, to find the area, we need to take the blue sector, the blue piece of pizza. That's what it's called, sector. So we need that blue sector, take away this pink sector, because we don't know the formula for the yellow bit, right? There is no formula that we know for that. But what we could do is we could find it by taking the area of the blue piece minus the area of the pink piece, because we do know the area of a sector. The area of a sector of a circle is a formula that we know from geometry class, right? It's right here. There's the area of a sector. So what we're going to do is we're going to find this little area. We'll call it change in area K, which I just realized I want to give it like a highlight or something. Right? I'm going to color it green. That's the change in area K right there. Okay, so let's find that. So the change in area K would be equal to the area of the large sector, which I've shaded in blue, minus the area of the smaller sector. Okay, sure. All right, so what's the area of the large sector? Well, it's 1/2 times something squared. The r squared is going to be the hard part. So we'll just write something squared and then times delta theta, right? Okay, so what's going on with this? What's the radius? Well, the radius is, let's think here. The radius of the large sector is this whole distance from here all the way to here. That would be the radius of the large sector. And that would be equal to r sub k star, right, which will get us out to this piece. So r sub k star plus 1/2 the change in r. So r sub k star gets me out to here, and then plus the half of that change in the radius, like that. Okay, so r sub k star plus 1/2 change in radius. That's the radius of the blue piece. All right, minus 1/2 something squared. You know where this is going, delta theta, right? So what about the radius of the small piece? Well, that's right here. The radius of the small piece is, well, r sub k star gets me out to this point, right? That's r sub k star. But I want to take away this section, right? R sub k star goes all the way out to here, and I don't want this piece of it. So I want to take away 1/2 of delta r. Right? So I'm deriving this formula, so you can't say you don't know where it comes from. So this is where it comes from. All right, and now we're just going to do some algebra, right? Some fancy algebra. First off, I noticed that delta theta and 1/2 is in everything, so I'm just going to pull that out to the front. 1/2 delta theta out times the whole thing. And then I'm going to distribute this. I'm going to FOIL it. So this would be r sub k star squared plus 2 times r sub k star times 1/2 delta r, which really means r sub k star times delta r, plus 1/4 delta r squared. That's just the first piece FOILed. Minus, I need the next piece FOILed. It's going to be r sub k star squared again, minus r sub k star delta r, plus 1/4 delta r squared again, like that, right? The outers and inners become these middle pieces right here, and then the lasts is that. Now you'll notice r sub k star squared minus r sub k star squared means this piece and this piece cancel. And furthermore, 1/4 delta r squared minus 1/4 delta r squared means that piece and that piece cancel. So this and this are gone, and this are gone. And all that leaves us with is 1/2 delta theta in front times r sub k delta r sub k star delta r plus r sub k delta r. So r sub k star delta r. And 2 times 1/2 becomes 1. So it becomes dA, right? Change in A, change in area, is r dr d theta. Oh, because this was delta theta r sub k star, right? So the change in area is, for a discrete value, is this, and therefore this is what dA is going to be. When you let the number of sectors go to infinity, this is what will happen. All right, let's put this all together into a formula. When we want to find this double integral, what we're doing is finding f of r theta, and then instead of dA, we would say it's what we just found, r dr d theta. All right, let's put it into practice. Let's not leave this video without having done one. So we're going to find this double integral for this section right here. There we go. Okay, so let's find it. Double integral xy. Okay, but x, I'm going to switch it to polar. So x is not x. X is r cosine theta. And y is r sine theta. And then dA is r dr d theta. Let me label everything for you. So this was x, this was y, and this piece was dA. Now, we need to figure out our limits of integration. We have this set up with dr coming first and d theta coming second. So theta, let's figure out theta. Theta goes from 0 over here all the way over, right? It starts at the pole and works its way around to pi over 2. So we're going from 0 to pi over 2. Naturally, we're in radians because, of course, we're in calculus and we're not dealing with vectors anymore. So 0 to pi over 2. Now, what about r? R, you got to think about a spoke coming out from the pole, because this is polar coordinates. So if you think about a spoke coming out from the pole, it's going to hit at an r value and then at another r value. So the first r value that it hits at is right here at r equals 1. And then it hits again out here at r equals 3. So there we go. So these are r values because they go with dr. These are theta values because they go with d theta. Remember that your double integrals are nested like that. All right, so let's rewrite all of this. So let's think. R times r times r, there's 3 r's there, so that's r cubed, cosine theta sine theta. dr, I'm actually going to write this 1, 3, dr, 0, pi over 2, d theta. All right, luckily we're doing r first, so it is easy because that's just 1/4 r to the 4th. So 0 to pi over 2, 1/4 r to the 4th from 1 to 3. And the cosine theta, the sine theta is just kind of sitting there, right? It's not really doing anything. And then d theta. You can put it in front. It can't go in front of the whole integral, but it could go in front of here, or it can go in the back. It's irrelevant. So, all right, so then I'm going to put in 3 and I'm going to put in 1. 3 going in would be 81. 1 going in would be 1. So this is really the integral from 0 to pi over 2. 81 take away 1 would be 80. So it's 80 divided by 4. Cosine theta sine theta d theta. D theta in blue. And then I'm just going to make Maple do that. I mean, technically we learned how to find that one in Calc 2. That was one of the integrals we learned how to find. However, we don't need to worry about it. So we're just going to make Maple do it. All right, so let's go look at Maple. Now this one I couldn't graph quite in the way that we wanted because we don't want this back half, but nevertheless that's what it looks like. So then when we put in the integral right here, we get that it's 10. And I checked my original integral as I had it written against that integral that I came up with after I had done the first step of integration. That's a way to check my answers with myself. And sure enough, both ways I find that it's 10. So this would be 10. Now keep in mind, if we knew that xy or xy in feet, for example, then this would be feet cubed because we're finding the volume. Unless, of course, we have some other context that we're trying to do this double integral in. But volume is the most common one for us. And for the record, the reason you want to switch it to polar is because think about what a nightmare this would be if it was in rectangular coordinates. Because these are the square roots of 1 minus x squared and the square root of 9 minus x squared. And so you'd have all sorts of a nightmare trying to do vertical or horizontal rectangles. They would be terrible. That's why you're switching to polar, because polar is actually tons easier. It's a little bit more work on the front end, but if you tried to do vertical rectangles or horizontal rectangles in any of this, it would be a nightmare. You'd have to do double sets of double integrals for starters. But it'd just be awful because the formulas are so terrible for circles. But in polar, it was a very easy integral to do. That's why we switched to polar.